I would like to introduce the heat capacity activity. Toward the bottom of page 1 is something about CP, which is the constant pressure heat capacity. We're not going to concern ourselves with that, so let's just keep moving on here. We're going to first, to calculate heat capacity, we want to calculate average energy. So we're going to calculate the average energy as was done in chapter 13. And then from that, we'll be able to calculate heat capacity. We're going to start with vibrational energy, and then move on to rotational, and compare the two. So here's the definition of the partition function in terms of vibrational energy. We already had that from chapter 13, so there's nothing new there. This equation here is the energy. That is kT squared over Q times the derivative of Q with respect to temperature. That's the average energy in terms of the partition function. So we're able to calculate average energy without having to uncalculate the population. Here's the actual definition. Energy, vibrational energy, average, equals kT squared over Q times the change in Q with respect to temperature. Notice that I had to add on the 0-point energy, because the 0-point energy is not zero for vibrational energy. You won't have to do that for rotation, but that's necessary for vibration. If you were to work out that function, this is what it would look like. It's kind of ugly, so let's just keep moving on. Graph here is the graph of average vibrational energy as a function of temperature. I've divided by Hartree because Hartree is a small unit of energy, and it makes these numbers visible on the y-axis. Remember that this is the average energy of a single molecule, and it's only considering the vibrational state. Notice at low temperatures, we have a plateau, and then as temperature increases, the vibrational energy can increase. This plateau is due to the 0-point energy. And in fact, if we were to add in the 0-point energy here, we would see where it lies. So there's the 0-point energy, this blue dotted line. And that's the initial plateau at low temperatures. Again, as the temperature increases, the energy increases, as it should. So, we want to calculate heat capacity. Heat capacity is going to be the change in energy with respect to temperature. And at high temperatures, you would expect it to be constant because this slope is constant in this graph. Alright, so let's go down and calculate this. Heat capacity, C sub V, which means constant volume. Constant volume heat capacity is equal to the change in internal energy with respect to temperature. And if you remember from class, internal energy is equal to, at any temperature T, equals internal energy at 0, plus, and this is the important part, for molar energy, it's Avogadro's constant times the average energy. This is the same average energy that we just calculated above. We want to look at the change in internal energy with respect to temperature. And that's going to be equal to Avogadro's constant times the change in this average energy with respect to temperature. So that's all we need to do, is just take the derivative of that expression above as a function of temperature. One point that we want to make is that the calculations we've been doing above have been for single molecules. But when we're dealing with thermodynamic quantities such as internal energy, we're interested in looking at quantities in the joules per mole range. So essentially that's what the Avogadro's constant is. it's multiplying our joules per molecule times Avogadro's constant so that we'll end up with joules per mole. So let's go down and actually calculate our heat capacity. And again, we're doing this for vibration. Okay, so here we are. Heat capacity constant volume, CV, is equal to Avogadro's constant times the change in energy with respect to temperature. That's just the general equation. Here we define it as a function. So CV, constant volume, vibrational energy is a function of temperature, is defined as this derivative, d of the average with respect to TT, molar temperature. If you want to see what it works out to be, this is a big ugly equation here, but you don't need to use this equation. It's already been defined in math class. This is just for fun, so you can look at what it looks like. Here's where we're at. Here's a plot. If you notice, in this plot, we start out at zero capacity, and then we move up towards this dotted line, which is the limit. To understand this plot, let's remind ourselves about what the energy plot looks like. So here's the energy, average vibrational energy per molecule. Again, I've divided by Hartrees because it's a small unit, and we can see the y-axis that way. I've compared the average energy. This is an exact quantity, the red line. I've compared it with the value for energy from the equipartition principle. Remember that for vibrational energy, there are two forms of energy per mode. We have the potential energy term, 1/2 kx squared, and we have the kinetic energy term from the motion, vibrational motion of each mode. So if we have a molecule, a diatomic molecule with one vibrational mode, the equipartition energy is given by kT. That's an approximation. This number here is exact. Notice that we have a 0-point plateau for the exact quantity, and then the equipartition quantity goes through 0. That's the quantity that would be expected if vibrational energy was classical. Okay? So now let's take a look at that and go back up to our heat capacity, and remember that heat capacity is the change in internal energy with respect to temperature. At low temperatures, the actual value, the change in internal energy, is going to be 0. It's going to be flat. There's no change in internal energy with respect to temperature. So it's going to be down at the 0. At higher temperatures, the slope is relatively constant. So at high temperatures, the value for heat capacity should be constant. And that's what we're seeing here at the heat capacity curve. If we were to take the derivative of kT versus temperature, if we were to take the derivative of kT versus temperature, obviously we just get K, constant. Heat capacity is a molar quantity, so we would want to multiply that by Avogadro's number. And this quantity is the same as R. So Avogadro's number times kV is just equal to R. Notice that N times K is just R, as we already know. That's why this is plotted up here. This dotted line represents R, the value for R, the ideal gas law constant. this heat capacity approaches the ideal gas law constant. Okay? Now let's calculate the heat capacity for rotational motion. So we'll really copy and paste from chapter 13 the parameters for rotational motion. What we need ultimately is the B value, B constant, to calculate the individual energy values, energy rotation. And then from that, we can calculate the partition function. And this is with a summation. And using a partition function, we can go back and calculate our energy as we did before, kT squared over Q, times the change in Q with respect to temperature. So we have our average energy. This is the average energy for the molecule. And remember that we'll have to multiply it by Avogadro's constant if we want energy per mole. Moving down, here's a plot. Plot of average energy is red. So here's the plot. So a very small temperature range, only 0.2 Kelvin. So you can kind of see the difference between the exact quantity given by the red curve and then KT, which is the equipartition principal energy, and that's given by the blue dots. Notice that the red curve is plateaued. It's about 0 in very low temperatures where only the lowest energy state is occupied. And then as temperature increases, it goes up linearly. Since it goes up linearly, you might expect that the change in energy with respect to temperature is going to be fairly constant. So let's see how that works out. Also, just for fun, we can remind ourselves what the energy of the vibrational motion looks like. So rotation, the exact energy, is just a little bit below the equipartition value, whereas for vibration, the exact energy is slightly above the equipartition value. That's because of the 0-point energy vibration. Let's take a look at this rotational energy and find out what the capacity is. Change in energy with respect to temperature. So here's the definition. CV, constant volume heat capacity, rotational motion, multiply it by Avogadro's constant, so you get a molar quantity, and it's a change in energy with respect to temperature, just like it was for vibration. Notice the graph. This is the graph of the rotational heat capacity as a function of temperature. Again, we're using very small temperatures, only up to 0.2. And for fun, we can compare that with, and I might need to squeeze things in a little bit here, compare that with the vibrational heat capacity. I'm making some noise. Alright. So here's the rotational heat capacity. Here's the vibration. Remember, the vibration started out at 0, slowly made its way up to R, the theoretical quantity due to the equipartition principle. Here we have something a little bit different. Rotational heat capacity starts out at 0, but there's a little bump where it actually goes above the theoretical, above the equipartition principle quantity. So what's the difference between rotational and vibration? You can pause the video and think about it. Okay, let's move down and see what's going on. Let's take a look at the population distribution for rotational energy. It's just equal to Boltzmann constant expression, exponential of the rotational energy divided by kT over Q, the partition function. And we can plot it as a function of the J quantum number. I've done it for very small temperatures, 0.1 Kelvin. 0.1 Kelvin. And 1 Kelvin. And what do you notice? go from 0.1 to 1 Kelvin, notice the population distribution. Because of degeneracy, rotational energy population distribution increases with increasing J quantum number. We can scroll down and look at the vibrational population distribution for contrast. Here's a population distribution at 300 Kelvin, and here it is at 100 Kelvin. I can only turn this up a little bit. Let's turn it up to 500 Kelvin. In both cases, the maximum population is at the lowest energy level. It's just as you heat it up, that distribution gets more spread out, as we know. In contrast, with rotational distribution, we need to squish this in just a little bit here. With rotational distribution, the actual maximum in the population plot shifts to higher quantum numbers. So at 0.1 Kelvin, the maximum population is in the first, so J equals 1 quantum level. At 1 Kelvin, the maximum population is in the 1, 2, 3, third quantum level. A shift gives rise to this unusual heat capacity behavior. You get this bump. And very low temperatures. The heat capacity versus temperature. So that's the main differences between rotational heat capacity and vibration. You'll also notice, of course, vastly different temperature range over which these are plotted, so you can kind of see the same sort of behavior. Be sure you understand these distinctions between rotation and vibration.